Assalamu alaikum wa rahmatullah. Welcome back. This is Dr. Muhammad Saad, and we are continuing our lectures on computer communications and networks. In the previous lectures and the previous videos, we finished our introduction. So we finished the introduction of this course, which corresponds to the introduction chapter of our textbook. Now, the chapter that comes next, chapter 2, is called physical layer. And as we have learned in our introduction, when we talked about the different layers, when we talked about the reference models, the protocol stack, like the OSI, Open Systems Interconnection Reference Model, or the TCP/IP reference model, we know that the first layer, layer 1 in our set of layers, is called the physical layer, which is responsible for the physical transmission of our bit sequence. So the physical transmission of our zeros and ones. So the main task of the physical layer is to make sure that the 0 is understood as a 0 and the 1 is understood as 1. And this includes physical layer techniques such as modulation, demodulation, detection, line coding, like finding out what is the waveform that corresponds to the 0 and the waveform that corresponds to the 1. So all these physical layer techniques are basically covered in a telecommunications course. So when you take Telecom 1, you will learn more about these things. That's why in our networking course, we go ahead and continue with chapter 3, the data link layer. So let me remind you of the main task of the data link layer. The data link layer is layer 2 in our protocol stack. So layer 1 physical, layer 2 data link layer, and the main job of the data link layer is to be able that the sender and receiver exchange frames. Instead of simply communicating bits, a raw bit sequence, no, we would like to be able to exchange frames error-free. So sending a frame from the sender and then receiving a frame without errors at the receiver. To get this accomplished, the data link layer needs to be doing some jobs like framing, and we will talk more about that in this video, in addition to error detection and correction, which is also known as error control. Framing and error control are the main two techniques of the data link layer, the main two tasks of the data link layer. In addition to this, the data link layer is also responsible for flow control, which is controlling the transmission rate. How fast is the sender sending so that we avoid overwhelming the receiver. So if the receiver gets overwhelmed with data and it's not able to deal with this data as fast as the sender is sending, the sender needs to slow down. This is called flow control. In a future chapter, when we talk about the transport layer, we will talk more about flow control, because flow control is one of the techniques which is done by the transport layer between end hosts again, and we will come into this. In this video, we will focus on framing and the error control. So let's try to remember our set of layers. So we have layer 1, the physical layer. Layer 2 is the data link layer. Layer 3 is the network layer, transport layer, and so on. So we know that the message that needs to be sent from host 1 to host 2. So if host 1 is the sending host, host 2 is the receiving host, and this message is coming from the top layer, the application layer of host 1, and then it goes down the protocol stack. It goes down the layers. We are getting headers attached, which we call encapsulation. And then at the receiver side, the physical layer is receiving basically this bit sequence, and then it goes up the layers to data link layer, to network layer, transport, and so on, until the application layer has the actual message. So we would like to distinguish here between the virtual and the actual communication, or virtual versus actual data path. And since we focus on layer 2, the data link layer, in this chapter, the data link layer of the sending machine is sending a frame which is received error-free by the data link layer of the receiving machine. So it appears as if there is a virtual communication channel between data link layer of host 1 and data link layer of host 2. And the job of this virtual path is to exchange a frame error-free. It is not true that the data link layer of the sender talks to the data link layer of the receiver immediately. However, the actual data path goes down the layers until we reach the physical layer. So the data link layer instead of sending the frame to the data link layer of the receiving machine directly, no, that frame is actually given to the physical layer, and the physical layer will be sending the ones and the zeros across the link connecting these two devices. The physical layer at the receiving machine is receiving the ones and the zeros, and that bit sequence is given to the data link layer of the receiving machine, which will be able, so that data link layer of the receiving machine will be able to take this bit sequence and recognize the frames basically that were transmitted by the data link layer of the sender. In addition to this, it will be able to detect and or correct any errors so the frame arrives correctly. So what is the idea of framing? So framing here, if I go back to our list of topics, framing is the first job of the data link layer. What do we mean by framing? Framing means the following. Imagine that we have a bit sequence, a sequence of ones and zeros. At the sender side, the start and the end of the frame is marked. So the sender is putting markers as to identify the beginning and the ending of the frame so that this frame is recognized by the receiver side. The beginning and the end of the next frame so that this frame is recognized by the receiver machine. So the receiver, instead of just receiving a bit sequence, which does not mean anything in particular, no, the receiver is able to identify the first frame and the second frame and the third frame and so on. So in short, framing means marking the beginning and the end of the frame, the start and the end of the frame, so that this start and end of the frame is recognized by the receiver, so that the receiver has the actual frame. This is very important as opposed to simply a bit sequence, because the frame, as you know, it contains a header, and this header would contain the address of the sender, the address of the receiver, and this is very useful for successful communication. And the trailer also contains the error control bits or the check bits that the receiver can use to find out if we have any transmission errors, and this would be our next topic in the next video, inshallah. So framing again. Framing, we want to talk more about framing, marking the beginning and the end of the frame so that the frame is recognized by the receiving machine. Before going ahead, let's try to remember the difference between the frame and the packet. You know, this is the sending machine and this is the receiving machine. The packet is the data unit which is created at layer 3, the network layer. To send this packet, it is given to the layer below, which is layer 2, the data link layer. The data link layer is adding a header and a trailer so that this whole data unit is called a frame. So what is a frame? A frame is a packet with an extra header and a trailer, so that as if we have an envelope which contains the packet. So you can think of the frame as the envelope which contains the packet with an extra header containing control information like the address of the source and destination, and a trailer which contains the error control bits, the check bits. Now, how is framing done? How is the beginning and the ending of the frame marked by the sender so that it is recognized by the receiving machine? We have 3 methods that we will talk about in this video: character count, flag bytes with byte stuffing, and flag bytes with bit stuffing. These are the main techniques that we will talk about, and let's start with character count. As you will notice, it's a very simple and intuitive mechanism. You know, the frame that we would like to send, if this is our frame, at the end of the day, that frame consists of bits. We can assume that each number of bits is actually a byte. You know, we have an 8-bit sequence which corresponds to a byte or a word, right? So we can always think of our frame as consisting of bytes or characters. Imagine that this is the frame I want to send here. This is the frame, 1, 2, 3, 4. So these are the 4 characters of my frame. How many characters do we have in my frame? I have 4 characters, right? So instead of just sending the frame as it is, no, we add 1 extra character at the beginning of the frame, which we call the character count character, and we just include how long the frame is. So imagine I want to send you a sentence, and my sentence has 6 words. Instead of just sending the 6-word sentence, no, I add an extra word at the beginning of the sentence, which contains number 7. And this number 7 says that my sentence has 7 words, including that word at the beginning. So when you see a 5 here, This is the character count frame. The character count character. It contains 5. So if the receiver receives this frame, it knows that this frame has 5 characters, including the character count. So 1, 2, 3, 4, 5. This is where the frame ends, and whatever I receive next must be a new frame. So the new frame also starts with a character count. So I know that my frame has 5 characters. 1, 2, 3, 4, 5. 5 characters, and this is the end of the frame. So frame 1 has 5 characters. Frame 2 has 5 characters. Again, 5 characters, including the character count. So the actual frame has 4. So this is the convention. This is the protocol. That's how we work, and that's how the sender and receiver understand each other. Now, the third frame, as you see, frame 3 starts with a character containing number 8. So this means that this frame has 8 characters, including the character count. So 1, 2, 3, 4, 5, 6, 7, 8, which means the frame ends here, and whatever comes next must be a new frame, which starts with a character count. It's also 8 in this example. This is just an example. So as long as the character count equals to 8, it means that our last frame also has 8 characters, 1, 2, 3, 4, 5, 6, 7, 8, and this is frame 4. So in short, each frame gets an additional character at the beginning, which includes how many characters do we have in the frame in total, including this newly inserted character count. So it works. As you see, it's very easy. If I'm the receiver, I receive a sequence of frames. I know that always the frame begins with a character count, and by just counting, I know where the frame ends, and if the frame ends, then the next frame begins, and so on. So it works fine. It works fine as long as we don't have transmission errors. So as long as we don't get any errors here in these characters, the receiver is detecting the frame correctly. But what happens? What happens if we have a transmission error? So here, in example B here, we have the same sequence of frames, but we have a transmission error. You know, this character was actually 5, but it was received as a 7. So this corresponds to a transmission error. Now, what will the receiver do when it wants to detect the frames? It sees a 5 here, so it says, okay, the first frame has 5 characters, 1, 2, 3, 4, 5, so that frame was received correctly. And now the next frame starts with a 7, so the receiver will think that the next frame has 7 characters, so it will count 1, 2, 3, 4, 5, 6, 7. So it thinks that the frame ends here, and what comes next, it would think, the receiver would think that this is the next frame, and so on. Obviously, the frames were not detected correctly. So only the first frame was detected correctly, but the second frame was not detected correctly. So the second frame actually ends with this character, but the receiver thought it ends with that character. So this frame was incorrect. And in fact, all following frames will also not be detected correctly. And this is a big problem. Okay, so that simple method of character count has basically a big problem. So the receiver will be totally out of synchronization in terms of the frames once there is one transmission error. And this is the problem with this method, character count. That's why it's not widely used nowadays, and we have other techniques. So the second technique that we would like to talk about here, this is the summary of the framing methods. Flag bytes with byte stuffing. Flag bytes with byte stuffing is the second method. What you see here, starting from the header and then the payload ending with the trailer, this is our frame. So this is our actual frame that the sender needs to send to some receiving machine. Now, how does the sender send this frame according to this method, flag bytes with byte stuffing? Now, this title has 2 parts, flag bytes and byte stuffing. Now, what is flag bytes? Flag bytes means simply at the beginning of the frame, we add a special character called the flag, or a special byte called the flag. Now, what is this flag byte here? It's an 8-bit sequence with a special pattern. It's an 8-bit sequence with a special pattern. In fact, that pattern is 0 followed by 6 ones followed by 0. So this special pattern here is reserved and called flag. And we have another flag at the end of the frame. So if I'm sending another frame, it would start with a flag and then followed by the frame and end with a flag and so on. So if the receiver sees that special flag It knows that a frame begins. So whatever comes next is the frame. And now when the flag comes again, this is the end of the end of the frame. Now, if we have a second frame, it starts with a flag again, and then the frame, and then it ends with a flag, and so on. Simple method. So we can summarize it by saying, before sending any frame, the sender adds a flag at the beginning and a flag at the end, and then it will send. When the receiver sees this special flag, and as part of the protocol, the receiver knows how the flag looks like. So what is this particular 8-bit pattern, which means flag? As I told you, it is 0 followed by 6 ones followed by 0. If this is seen, it means this is the beginning of the frame. And then whatever comes next is the frame. When I see another flag, it means this is the end of the frame. Now, if I see a flag, it must be the beginning of the next frame, and so on. Things are perfect. However, we have a problem. What is the problem? The problem is if the frame itself, the data part of the frame itself, contains a flag, contains a pattern similar to the flag by coincidence. As an analogy, colleagues, imagine that I'm sending you some sentences, right? I'm sending you some sentences, and we agree together that before each sentence I have to say flag, and after the sentence I say flag. So let's say I want to send you the following sentence. I hope that you enjoy this video. So instead of just sending the sentence, I say flag. I hope that you enjoy this video, flag. Now, if I need to send you a second sentence, I also start with a flag and end with a flag, and so on. But what happens if my sentence, by coincidence, contains the word flag, right? So what if my sentence is, we have to respect our country's flag, right? So I insert a flag at the beginning and the flag at the end. So I will say flag, we have to respect our country's flag, flag. Now, when you see this flag, which is actually part of the data, you may think this is the end of the frame instead of being an actual part of the data. So the problem is if that pattern flag appears inside the frame. So what do we do with that? And this is the second part of the title that we call byte stuffing. We solve this problem in a very easy way. We have the description here in the slide, but we use this picture to illustrate. The solution is very easy. So flag is a special character. Actually, this method, flag bytes with byte stuffing, has a second special character that we call escape. So flag is a special character with a specific bit pattern, and escape is a second special character with another special bit pattern that the sender and receiver agree upon. So how do we use this escape? We use this escape as follows. So first of all, this is our frame from the beginning until the end of the frame that we need to send. How does the sender send this frame? First of all, it adds a flag at the beginning and a flag at the end. This is to begin with. This is the easy part. It happens all the time. However, before sending, the sender would go through the data, would go through the frame itself. And if it sees a flag pattern in the data itself, it will add an escape before the flag. Insert or stuff an escape before the flag. And here we have numerous examples on how this happens and how the receiver can recognize that the flag actually is part of the data and not an actual flag that says this is the end of the frame. So here in this example, what you see on the left here is the frame, is the data frame. So here we have a frame with 3 characters, A, flag, B. Character A, character flag, character B. This is the frame that we need to send. What does the sender do? The sender adds a flag at the beginning and a flag at the end, which is not shown here. So this is the easy part. It happens anyway. But this example here focuses on the byte stuffing. Okay, so we have a flag at the beginning and a flag at the end. But before sending, the sender goes through the frame, and whenever it sees a data flag, it will add an escape before the flag. So that's why instead of sending A flag B, the sender would send A escape flag B. That's in addition to the flag at the beginning and the flag at the end. Now, how does the receiver operate? What does the receiver do? If the receiver receives this frame, obviously flag at the beginning and flag at the end. So flag at the beginning means beginning of the frame. As long as it's just a flag without any escape or anything, it means beginning of the frame. And now it will read the data, A escape flag B. Now the receiver works as follows. If you see an escape followed by a flag, the escape is removed. If this escape is removed, what is the data that the receiver has just recovered? The same as the actual frame that the sender wanted to send, A flag B. Now it will continue. If it sees a flag alone without an escape, it means this is the end of the frame. So if the receiver sees a flag alone without any escape or anything, it means beginning of the frame, and then obviously we have to have the frame, and then the next flag is the end of the frame, and so on. Inside the frame, if there is any flag with an escape before it, the escape must have been inserted or stuffed by the sender, so the receiver just removes it. Now, the other examples just show you all other possibilities so that you make sure that this method actually works. Now, you may ask me, what happens if the data contains an escape? What happens if the data contains an escape? It's by chance, by coincidence, it contains an escape character. Okay, so the frame the sender wants to send contains character A, character escape, character B. Now, to send this frame, we have a flag at the beginning, flag at the end, always. However, before sending, the sender goes through the frame, and if there is an escape, we insert another escape before it. Now, how does the receiver operate? It will read A. It will find escape followed by escape. As long as we have an escape followed by an escape, so this one needs to be removed because it was stuffed by the sender for sure, so we recover the actual frame. Now, if the frame contains escape followed by flag, so the data frame itself contains character escape and character flag. How does what does the sender do? It adds an escape before the first escape. It adds an escape before the flag, right? So instead of sending A escape flag B, it would send A escape 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 flag B. However, the receiver knows the protocol. The receiver knows how things work. So the receiver will go through the frame. It says an A, okay, this is an A, and now escape followed by an escape, so the first escape is removed, and then it will see an escape followed by a flag, so the escape is removed. So once this is done, the receiver has recovered the actual frame, which is A escape flag B. Now, the last example is if the actual data frame contains two escapes after the other. By coincidence, by chance, so the frame has character A, character escape followed by character B. What does the sender do? It goes through the frame. If I see an escape, I add another escape. Now, if I see the second escape, I add also an escape before the escape. So for each one of these two escapes, we add an escape before it, and then we send the whole frame. Now, if the receiver receives this sequence of characters, it will go through the frame. A is okay, and then escape followed by escape, the escape is removed, and then escape followed by another escape, the first escape is removed, so we recover the actual frame that was sent, A escape B. Now, that's precisely what happens at the sender side and at the receiver side. So at the receiver side, to summarize what the receiver does, if the receiver sees escape followed by flag, remove the escape. If the receiver sees escape followed by escape, remove the first escape, and then we have recovered the actual frame. Always at the beginning of the frame, we have a sending flag, and at the end of the frame, we have the start flag, and at the end, we have the end flag, and this happens all the time. Now, it works well, as you have seen. So we cover all the cases here. It works well. However, we have some disadvantages. The first disadvantage is that we are dealing with special characters, flag and escape, and these characters have 8 bits, right? So this technique itself is closely tied to using 8-bit characters. This is a typo, 8-bit characters. What if my frame consists of characters that have different lengths or not necessarily 8-bit characters? Then this method might not be very suitable. Another disadvantage actually is that this insertion or this stuffing of an escape, how long is the escape? 8 bits. So whenever I see a flag in the middle of the frame, I have to insert 8 extra bits, which is not part of the data, but it was necessary so that the receiver knows that what you see here is not an actual flag that basically marks the end of the frame or the beginning of the frame. No, this is part of the data. So we have to add 8 bits. Can we do better than that? Yes, we can do better than that. Instead of adding an escape, instead of inserting an escape which has 8 characters, we can actually get along with adding only 1 bit. So sorry, instead of adding an escape which consists of 8 bits, we can actually add only 1 bit, and this will be done in the next technique, which is called start and end flags with bit stuffing. So you notice that these two titles are almost the same. So flag and end bytes with byte stuffing, and this is start and end flags with bit stuffing. So the only difference between the second mechanism and the third mechanism is in the stuffing here. Byte stuffing versus bit stuffing. Byte stuffing means we add an escape. Bit stuffing means we add only 1 bit. So this figure here, my illustrative figure, summarizes how this third technique works, flag bytes with bit stuffing. It works as follows. So again, if this is our frame, before sending the frame, we add a flag at the beginning and a flag at the end. So far, this method is exactly the same as the method before. We have a flag at the beginning and a flag at the end. However, let me just remind you, what is the flag? It's an 8-bit sequence, 0 followed by 6 ones, followed by 0. 0 followed by 6 ones, followed by 0. And then we send the whole thing. If the receiver sees the flag, it knows this is the beginning of the frame. It will go through reading the frame, and then if it sees another flag, it must be the end of the frame. And if there is a flag after it, it must be the beginning of the next frame, and so on. Now, what is the problem? The problem is exactly the same. What happens if inside the frame, we have a pattern similar to the flag? In other words, what happens if this frame what happens if this frame contains this pattern 0 followed by 6 ones followed by 0? Now we would like to add something that tells the receiver that what you see is not a flag, it's actually part of the data, and this is the idea of bit stuffing. Now how does bit stuffing work? The sender goes through the frame. If it sees 5 consecutive ones, what is the main characteristic of this flag? Is the fact that it has 6 ones. Let's make sure we never have 6 ones in our data. We never have 6 ones by a very simple rule that the sender and the receiver agree upon. It's part of the protocol, it's part of this method. So what does the sender do? Again, at the sender side, if the frame has 5 consecutive ones, 5 ones, one after the other, stuff or add is 0 after the 5 ones. So it becomes impossible to have something that looks similar like the flag in our frame. So this is what happens at the sender. If there is any 5 ones, add a 0 and then transmit. The whole thing is transmitted. If the receiver receives the frame, of course, it recognizes the start and end of the frame through the flags, which has 0, 6 ones followed by 0. Of course, we don't add the 0 here. This additional 0 is not inserted here because the whole idea is that we keep the flag untouched. This is only done in the data frame so that we make sure that inside we have nothing that looks like the flags, right? So again, the receiver sees the flag, so this must be the beginning of the frame, and then it goes through the frame, reading it bit by bit. If it sees 5 ones, so this is how the receiver works. If the receiver sees any 5 ones followed by a 0, that 0 is removed because it must have been definitely inserted or stuffed at the sender side. So that's how it works. Here in this slide, we just tell you that start and end flags with bit stuffing, it's a technique that has a flag, and that flag consists of 8 bits, 0 followed by 6 ones followed by 0. We always add this flag at the beginning and end of the frame so that we mark the beginning and the end. However, bit stuffing works as follows. At the sender side, if there is 5 ones followed by, sorry, at the sender side, if we have 5 ones, the sender automatically adds a 0 after the 5 ones in the outgoing data stream, in the outgoing frame. How does the receiver work? If the receiver sees 5 ones followed by a 0, automatically delete the 0, and this works all the time. Here we have some examples. So if what you see here in A, if what you see in A is the data frame that needs to be sent, and this is the data frame as a binary sequence. Of course, to send this frame, we have to add a flag at the beginning and a flag at the end, and this is something easy that we're not showing. This example focuses on the bit stuffing. So we have a flag at the beginning and the flag at the end, but before sending, the sender needs to go through the data. If the sender sees 5 ones, 1, 2, 3, 4, 5, add a 0, which is not part of the data. It was added or inserted by the sender artificially and deliberately before sending. And now if we continue, we have another 5 ones, 1, 2, 3, 4, 5. We add a 0, and then we have another 5 ones, 1, 2, 3, 4, 5. Actually here, 1, 2, 3, 4, 5. We add a 0, 1, 2, 3, 4, 5. We add a 0, and then 1, 2, 3, 4, 5. We add a 0. That's why after this 5, which appears here, we add a 0, and then we simply have the rest of the data, which is 1, 0, 0, 1, 0, 1, 0, 0, 1, 0. So I think I may have confused you here a little bit. So let me repeat again. So the sender goes through the bit sequence. If it sees any 5 ones, it will add a 0. 1, 2, 3, 4, 5. We have a 0. 1, 2, 3, 4, 5. We add another 0. 1, 2, 3, 4, 5. We add a third 0, and then comes the rest of the data bits, which don't contain any 5 consecutive ones. So this will be the sequence transmitted by the sender. Now, if the receiver receives this frame, of course, there is a flag at the beginning and the flag at the end that mark the beginning and the end of the frame. But when the receiver receives the frame itself, what does it do? It goes through the bits. If it sees any 5 ones, 1, 2, 3, 4, 5, followed by a 0, remove the 0. 5 ones followed by a 0, remove this 0. 5 ones followed by a 0, remove the 0. So all the stuffed bits were removed, and what we recover is actually the same as the transmitted sequence, which is the sequence intended to be transmitted by the sender. So we have bit stuffing at the sender side, bit destuffing, which is removing of the extra zeros at the receiver side, and we are all good. Thank you very much, and in the next video we will talk about error control. See you then. Assalamu alaikum wa rahmatullah.